Welcome to The Explainer. In science, you're constantly dealing with numbers that are either astronomically huge or impossibly small. So, how do you even write them down correctly, let alone use them in a calculation? Well, it turns out there's a whole system, kind of like a set of hidden rules, that makes it all possible. Let's dive in and uncover what they are. So, to really get a feel for the problem we're talking about, let's start with a question. How many atoms do you think are packed into just one single gram of hydrogen? Go ahead, take a guess. The answer is this monster of a number, 602 sextillion. I mean, just look at all those zeros. Can you imagine trying to write this out every single time you needed it? Or worse, punching it into a calculator? You're just begging for a typo that could throw off your entire experiment. And that brings us to the core question, right? How on earth do scientists manage these numbers without completely losing their minds? Well, the answer lies in a few incredibly smart, really elegant tools they've developed over the years.
Okay, so our first stop is figuring out how to wrangle these extreme numbers. And to do that, we're basically going to learn a new language, a language designed by scientists for science.
That language is called scientific notation. And the idea behind it is actually pretty simple. You rewrite any number, no matter how big or small, as two parts. First, you have a number between 1 and 10, that's called the coefficient, and second, you multiply that by 10 raised to some power. So that massive number of hydrogen atoms we just saw, it becomes a nice, clean, simple 6.02 times 10 to the 23rd. Much better.
And here's the thing, this system isn't just for gigantic numbers. It works just as beautifully for the incredibly tiny ones. For example, here's the mass of one single water molecule in grams. Again, it's a total mass of zeros. It's tough to even read, let alone work with. But when we use the language of science, it becomes simply 2.99 times 10 to the negative 23rd grams. See? That's the real power of this notation. It's concise, it's clear, and it can handle everything from the size of the universe down to the mass of a molecule. So the whole key is just understanding the exponents. Here's the rule of thumb. If you see a positive exponent, you know you're dealing with a big number. A negative exponent? That tells you you're working with a really tiny number, something smaller than 1. It's as simple as that.
Okay, so we figured out how to write the numbers. Awesome. But that's only half the battle. Now we have to ask a different question. How do we know if a measurement is any good? And this brings us to two words that we all use interchangeably in everyday life, but in science, they mean two very, very different things: accuracy and precision. Let's break this down because it's super important. Accuracy is all about being correct. It's how close your measurement is to the real, true, accepted value. Precision, on the other hand, is about being consistent. It's how close a bunch of your own measurements are to each other. In other words, can you get the same result over and over again? The absolute best way to visualize this is the classic dartboard analogy. If you throw your darts and they all land in a tight little cluster right on the bullseye, congratulations, you've got good accuracy and good precision. But what if your darts are all clustered together but way over in the corner? Well, that's good precision, you're consistent, but your accuracy is terrible. And if your darts are just all over the board, yeah, that's poor accuracy and poor precision. Definitely not a great day at the lab. So let's take this idea into a real lab scenario. Imagine you're measuring the boiling point of water. We all know the true accepted value is 100.0 degrees Celsius, but your thermometer, which gives you your experimental value, says it's 99.1 degrees. So what do we call that little gap between the two?
In science, that difference has a specific name, error, and it's a simple calculation, just your experimental value minus the accepted value. So in our water example, the error is negative 0.9 degrees Celsius. This is a really important number for figuring out just how accurate our measurement was.
Now, this brings us to what might be the most important concept of all for handling scientific data: the language of certainty. Because every single number a scientist writes down tells a story about how much you can actually trust that number. And this is where we need to talk about significant figures. Significant figures, or sig figs for short, are basically all the digits in a measurement that you know for sure, plus one final digit that's a reasonable estimate. Think of it like this. They're a direct reflection of how precise your measuring tool is. A cheap plastic ruler and a high-tech laser are going to give you very different numbers of significant figures. So how do you know which digits actually count as significant?
There are a few core rules. The main idea is figuring out which zeros were actually measured and which ones are just there to hold a place. For instance, any zero that's sandwiched between other numbers always counts. And zeros at the very end of a decimal, they count too because they're telling you exactly how precise your measurement was.
But here's where things get a little tricky. We have something called the ambiguous zero. If I just write down 300 meters, what does that mean? Did I measure it to be exactly 300, or is it just a rough estimate and those zeros are just placeholders? Is that one significant figure, or is it three? Based on the number alone, we have no idea. And this brings us back to why scientific notation is just so brilliant. It completely solves this problem. If I write 3.00 times 10 to the 2, I am telling you with no doubt that there are three significant figures. If I write 3 times 10 to the 2, I'm saying there's only one. All the ambiguity is just gone. It's pure clarity. All right, so now we know how to read and write numbers and understand their certainty. The final piece of the puzzle is, how do we actually do math with them? Well, there are rules of engagement for this too, and they're all designed to stop us from accidentally making our answers look more precise than they really are. When you're adding or subtracting, the rule is pretty straightforward, and it's all about the decimal places. Your final answer has to be rounded to the same number of decimal places as the measurement in your problem that has the fewest decimal places. You just can't be more precise than your weakest link.
Let's look at this rule in action. We add up these three measurements, and our calculator spits out 369.76. But wait, take a look at that middle value, 349.0. It only has one digit after the decimal, which makes it our least precise measurement, our weakest link. So our final honest answer has to also be rounded to one decimal place, 369.8 meters. Now, for multiplication and division, the rule is a little different. Here, we're not looking at decimal places anymore. Instead, we're counting up the total number of significant figures in each measurement. Your final answer has to be rounded so it has the same number of sig figs as the number you started with that had the fewest sig figs. And you know, all of these calculation rules, they really just boil down to this one big idea. This is the golden rule of scientific math. You can't magically create precision out of thin air just by using a calculator. Your final answer certainty is always limited by your least certain measurement. So what's the ultimate takeaway here? It's that numbers in science aren't just numbers. They are statements. They tell a story about confidence, and they carry hidden information about their own limits. And that leaves us with a final question for you. The next time you see a number, whether it's in a news article or on the back of a cereal box, ask yourself, how much of it can I truly trust? Thanks for watching The Explainer.